squared. We also talked about the negative binomial distribution, or neg-bin RP. So this is a sum of R IID geometric P, and the probability that TR is K has this kind of complicated looking formula, but it's not that hard if you think about it. So we require the kth trial to be a success, so probability P. And in the previous K minus 1 trials, hence we require R minus 1 successes. So we have K minus 1 choose R minus 1, P to the R minus 1, Q to the K minus R times P. The expectation is R over P, and the variance is RQ over P squared. Those are easy to get since basically TR is W1 plus W2 up to WR. So today we're going to finish section 3.4 on the minimum of independent geometrics. We'll then do the Poisson distribution and Poisson random scatter, also known as Poisson process, and we'll begin to talk about something called Poisson thinning. So minimum of independent geometrics. Say Adam, Beth, and John independently flip a P1, P2, P3 coin respectively. Let X be the number of trials until Adam, Beth, or John gets ahead. So for example, X would be 3 if, for example, John gets TTH and Adam and Beth both get TTT. So X1, X2, X3 are all geometric with P1, P2, P3 respectively. So what's the probability that Adam, Beth, or John get ahead? So P is the probability that Adam or Beth or John get ahead, which is 1 minus the probability that Adam, Beth, John don't get ahead, which would be 1 minus Q1, Q2, Q3. What's the distribution of X? So you can think of it, it's a geometric 1 minus Q1, Q2, Q3. So every trial, you're flipping a coin. Actually, you're flipping, Adam, Beth, and John are all flipping their coin. And you have a success if any of them get ahead, and you have a failure otherwise. So that finishes 3.4. Section 3.5 is about the Poisson distribution, or Poiss mu. So X belongs to Poisson mu. Then the Poisson formula is given here, and that's just the same formula that we had been working with in an earlier chapter. So let's find the expectation invariance. So we want to remember Taylor's series for e to the mu is 1 plus mu squared over 2 factorial and so on. And so we'll just use the definition of expectation. So the expectation is the sum over all of the outcomes, which is 0 to infinity, k times probability that x is k. So that's the sum from 0 to infinity, k e to the minus mu to the k over k factorial. And we could write that starting it from k equals 1, since the k equals 0 term is just 0. So then also we can write k factorial as k times k minus 1 factorial. Then the k's cancel as shown, and you can also pull out everything that doesn't have a k in it. In other words, mu e to the minus mu. And you get an expression that is precisely the Taylor series for e to the mu. So we have mu e to the minus mu times e to the mu, which is mu. So just note that this makes sense, since remember that binomial NP is an approximation of Poisson when n is large, p is small, and NP converges on mu. So remember, this is like the eighth row of this grid where we had all of these binomials for different p's, and so the left-hand side is for small p's, and that's approximately Poisson on the left here. We'd also expect the variance to be mu, since NPQ, the variance of so the variance of binomial converges to mu q, which is approximately mu, since as p goes to 0, q goes to 1. So the variance of x should be mu. But let's check this. So the variance of x we write as expectation of x squared minus expectation of x quantity squared. And we're going to want to use an expression for the expectation of x minus 1. So to do this, we just do a trick where we subtract expectation of x and then add expectation of x. And calculating the expectation of x minus 1, we just use the definition and pull out an e to the minus mu. And then we get the Taylor series for e to the mu again, and we find that it's mu squared. So then the variance of x is mu squared plus mu minus mu squared, which is just mu. So I asked you guys an exercise, let x be Poisson mu, find the expectation that x minus 1, find the expectation of x times x minus 1. And some of you just try to do that from the definition, which is fine, but it's easier to just distribute the expectation. And notice that you can't write expectation of x times expectation of x plus 1, since x and x plus 1 are not independent. And so we write the expectation of x squared as the variance of x plus expectation of x quantity squared. And that gives us 2 mu plus mu squared. So next on to Poisson random scatter. So Poisson NP is approximately binomial NP with large N, small p. So Poisson comes up when we model situations with low probability independent trials. So for example, let x be the number of calls coming into a hotel reservation center in 10 minutes. So say mu is 10 calls. Sorry, this is per 10 minutes. Okay, or let's just say mu is 10 calls. I'll just say in 10 minutes. Okay, so so here's some picture. That was on average, we get 5 calls per minute, but in this particular 10 minutes, we got, I think, 8. And the trials of calls, so these hits where we get calls should look random, not clustered, since we have independent trials all with the same P. We can subdivide the time that we have, say, into seconds, for example, or even smaller time intervals where we'll be assured that we only get a single call per time interval. So the Poisson random scatter assumptions are that 1, no time interval gets more than 1 call, and this you can assure by having very small time intervals. And 2, have NIID Bernoulli P trials, all with the same P, with mu equals NP, large N, small p. Okay, in other words, all calls are independent of each other with the same probability. So mu is the mean number of calls in t minutes. So let lambda be mu over t, be the intensity or rate of calls per minute for a Poisson random scatter. For example, lambda is 5 over 10, or 1/2 calls per minute in the above example. So we did a concept test. Which of the following can be modeled as a Poisson random scatter with intensity lambda greater than 0? So it is A. So it is A, the number of blueberries in a 3 cubic inch blueberry muffin. Since you can think of each morsel as just containing a single blueberry, we can make the morsel small enough. And yep, and so that would be a Poisson random scatter. The number of patients entering a doctor's office in a 24-hour period wouldn't, because lambda isn't constant here, right? You would expect a higher rate of patients entering in the middle of the day than in the middle of the night. The number of times a day a person feels hungry is clustered around traditional meal times. And the number of air pulses counted every second from cars driving over an empty rubber hose lying across a highway between noon and 1 p.m. violates a couple ways. So one is because our trials are every second, it's very conceivable that we'll get multiple air pulses in a second. And secondly, that the pulses come in pairs, because you have the front and rear wheel driving over the hose. So so if you just imagine what the scatter would look like, it would come in pairs, which wouldn't be random. Continuing with the blueberry muffin, we have a tub of blueberry muffin batter with lambda equals 2 blueberries per cubic inch. A muffin is 3 cubic inches. On average, how many blueberries per muffin? Well, it would be 6 blueberries. Let x1 be the number of blueberries in the first muffin. So x1 is Poisson 6. There's another size 4 cubic inches from the same tub of batter. So let x2 be the number of blueberries in the second muffin. And actually, I rewrote this here, so sorry about that. Find the probability that there are 5 blueberries in each muffin. So x1 is Poisson 6, x2 is Poisson 8. So we want the probability that x1 is 5 and x2 is 5, which is, and these are independent. So we just have the product of these Poisson formulas. Find the probability that you have 10 blueberries total in each muffin. So here we'd have x1. So 8. So we have 10 blueberries total in both in both muffins. Not in each, but in both. In both muffins together. So the key here is to remember that x1 plus x2 is Poisson 14, which is 6 plus 8. And so the probability that x1 plus x2 is 10 would be e to the minus 14, 14 to the 10 over 10 factorial. Finally, just briefly, we talked about Poisson thinning. This is a fairly easy idea. Say that you have a Poisson process, which is cars arriving at a toll booth with a rate lambda is 3 arrivals per minute. Of the cars arriving, 60% are Japanese imports. So I've written the Japanese imports in purple and the non-Japanese imports in green. So not surprising that the Japanese imports and the non-Japanese imports are each separately Poisson processes with intensity rates P lambda for the Japanese and Q lambda for the non-Japanese. Okay, and we'll do an example of this next time. Have a great weekend.